Okay, let's start our seminar. And today I'm a speaker here, and my talk will be devoted to Ruijsenaars duality in classical integrable systems, namely to dual systems to BCD Toda chains. Yeah, and first of all, I will briefly remind you what is Toda chains and how they are related to root systems. After that, I review the way of Hamiltonian reduction, which is the main tool to prove the duality. And the last part will be quite technical when I explain what are goldfish systems, which are dual to Ruijsenaars dual to Toda chains, and how one can compute their Hamiltonians explicitly. And let us start with Toda chains. Yeah. So we deal with classical integrable systems of classical mechanics. We will have n coordinates and n momenta of particles with canonical Poisson brackets. And the dynamics of these systems are driven by one Hamilton function, which is the energy of this system of interaction particles. And canonical equations of motion say that time derivative of any value is a Poisson bracket with this Hamilton function. And what is classical integrable system? In classical integrable system, we have n such functions, where n is the size of the system, is the number of particles. And we have n independent Poisson commuting functions hi. Either of these functions can be used as a Hamilton function of this system, and all other functions have zero Poisson brackets with it. So they are just conservation laws for this Hamiltonian. And for example, for this system, for this Toda chain, a system of particles where only nearest neighbors interact in exponential way, we can construct these n-independent Poisson commuting functions. And the first of them will be a simple one, which is total momentum of the system. The second one is just a Hamiltonian. And all others will start with L's power of momentum and have some lower terms, which are non-trivial. So, but we know that there exists such a set, and this system is classical integrable one. So, and in this case, we have these n-independent Poisson commuting values, and we can solve equations of motion of our systems in quadratures. And in usual differential equations, you will need 2n minus 1, because you have 2n differential equations. But here you need only n. Okay, so, and one can notice that here we have this exponential interaction between particles. And this Toda chain relates to a system, relates to a type root system and to Lie algebra SLN. And sum here is can be interpreted as a sum over simple roots of SLN Lie algebra. And as well as this system is integrable, we know that we have more integrable systems of the same type, which are also known as Toda chains or generalized Toda chains, which relate to classical root systems. So, and we have here the interaction, which is also exponential, but here we have some of our simple roots of our Lie algebra. And for example, in type C, we will have the Hamiltonian, which is just type A Hamiltonian, plus some additional part which relates to the nth root of C system. And the same we have for B and D, and even for exceptional cases. Okay, so let me now explain what is a Ruijsenaars duality. What is my talk about? We have this classical integrable system. So we have n commuting Hamiltonians and commuting functions of coordinate and momentum. But on the same phase space, one can consider a trivial integrable system, which everyone can construct easily. So we can just use our coordinates as Hamiltonians. And this dynamics is trivial, so it's not an interest in integrable systems. The dynamic is just linear, and it can be easily resolved. But Ruijsenaars duality says that for some cases, we can have two integrable systems on the same phase space, and Hamiltonians of one integrable system will relate to coordinates of the other one. And coordinates of this system will relate to Hamiltonian system. Or more explicitly, action variables of one integrable system will be the coordinates of the other one, and vice versa. So, and it is a well-known duality in integrable systems. We have a lot of examples. And for example, we have this duality square for integrable system of Cauchy-Binet family, where rational Cauchy system is self-dual under this duality. Trigonometric Cauchy is dual to rational Ruijsenaars system. Trigonometric Ruijsenaars is dual to itself as well. And we have also some dualities with elliptic case, which are non-well studied. But we have the same feature here, that some trigonometric dependence become rational. So we have some exponential dependence on momenta in this system, and we will have trigonometric dependence of coordinates in this system. And we have a rational dependence, just a polynomial dependence on momenta here, and we will have a rational dependence on coordinates here. So we can exchange the rational and trigonometric, we can exchange rational and elliptic, and so on. So, and it is well studied for Cauchy case. We have a lot of examples here. So we even have some knowledge about elliptic systems, but for a few number of particles. Yeah. So, but in Toda chain, we also have this duality. And the Ruijsenaars dual system to the Toda chain is named Goldfish model. It was introduced by Cauchy. And in Toda case, we have sum of particles with the momenta, and our Hamiltonian was p squares over 2. So we had just a Hamiltonian, which is non-relativistic one. And interaction between the coordinates was exponential. And here we have a dual system, which has exponential dependence on momenta, so it is a relativistic system, but rational on coordinates. In the duality set of the previous picture, it can be laid as well, because this open Toda chain relates to trigonometric Cauchy system, and it can be obtained by Inozemtsev limit. So when we scale our interaction constant and change our coordinates as well, and we will have in Inozemtsev limit of trigonometric Cauchy system, we will get this open Toda chain. And this system is related to rational Ruijsenaars system by Ruijsenaars duality, which is in a strong coupling limit. When we have this eta goes to infinity, we will get a rational Goldfish model. Yeah. So, and this system as well appears to be Ruijsenaars. Yeah. And it was proved for a case by Feicher, who will be a next speaker of our seminar in a week later. And today I will focus on a BCD case, mostly and C case as the most simple one, and show how this duality works for other root systems. Yeah. So, and it is a brief introduction of this duality. Okay. What is the main tool which we use? It is Hamiltonian reduction. So what is the idea? we will have a simple dynamics on a large phase space, and our integrable system will appear on a reduced phase space of a lower dimension. And our non-trivial Hamiltonians of our integrable system will be got from the simple Hamiltonians on the top. So what we have here, we have a symplectic manifold, which is a manifold with a two form, which is non-generate and closed. And this symplectic form, it is non-generate, so we can define its inverse, which is a bivector field. And this bivector field just defines a Poisson brackets on functions on M. And this symplectic form, as it's not generate, also defines a mapping between one forms and vector fields here. So we can just put vector field into this two form and get some one form. And it is one-by-one correspondence due to non-generacy. And we have this symplectic manifold, and we have a large symmetry here. We have a Lie group acting on this symplectic manifold. And when we have an action of a Lie group on a manifold, our elements of Lie algebra will map to vector fields on this manifold. We can just get one parametric group and see a tangent vector field. And a natural action of a Lie group on this symplectic manifold is called Hamiltonian action. So it's not just an action of a Lie group, but it has additional property that for any Lie group element, this vector field, this vector field Vxi, will be Hamiltonian vector field. So we have here one form for this. For any vector field, we have one form. An additional requirement here that it will be not any one form, but an exact one. So it's a differential of some function. And this function is called Hamiltonian of this vector field. So in the physical notation, so we just raise the index and obtain an exact differential. And in this Hamiltonian action, not only all these vector fields are Hamiltonian vector fields, but we also have a momentum map, which is a dual operation. It's a map from our symplectic manifold to a dual to Lie algebra of group acting here, which value on Xi is just a Hamiltonian of this action. Yeah. And this construction of Hamiltonian action allows us to reduce the dynamics from a larger system to a smaller one. So we have this momentum map, which maps from our symplectic manifold to a dual to Lie algebra, and fix a value of this momentum map. So now we can construct this space M lambda, where mu minus 1 of lambda is a lever surface of this fixed value. And we have a stabilizer of this lambda, which acts on this mu minus 1 of lambda. And this mu lambda is called reduced space. And if we put some conditions on our action, it will be a symplectic space or even a symplectic manifold. And dimension of this space will be lower. So here we fixed some elements. So it's dimension of G constraints. And here we have factor by dimension of G lambda. So the dimension of this mu lambda is dimension of M minus dimension of group and minus dimension of stabilizer. And if we have this nice lambda with a large stabilizer, we can reduce our dimension of our system a lot. And under this Hamiltonian action, which was in the previous slide, under this Hamiltonian action, the symplectic form conserves. So this Hamiltonian action doesn't change the symplectic form always. So we can define a symplectic form on this reduced space as well. So we have this mu minus 1 of lambda, which is a submanifold in M. And we have a projection of mu minus 1 of lambda to our reduced space. So it is also a theorem of Hamiltonian reduction that the symplectic form in this case can be just defined via these pullbacks. And as well, if we have some invariant function on a top, it can be always reduced to a function on a reduced phase space. So we have, if we have this function which is invariant under group action, we also can do these pullbacks and define a function on a reduced phase. And what is a source of integrable system? So in integrable system, we have two n-dimensional phase space, and we need to have n commuting Hamiltonians. And it is a lot. So, and a way to construct it, let's consider a large first phase space in the beginning and reduce to the smaller phase space. Let's choose this lambda and let's have a large stabilizer. So we have a smaller dimension, but all invariant functions which was commutative on the top will commute on the bottom as well. So if we have enough simple but commuting function here, we will have an integrable systems on the bottom. So and it is the main thing in Hamiltonian reductions. Okay. So, and let us fix some notations here. For Lie groups, we will have some matrix complex Lie group BCD types, or even A type. This is a Lie algebra, and we have trace which identifies a dual space to a Lie algebra. And for this Lie algebra, we have a decomposition: positive roots, negative roots, and cartan. And let us denote this n plus and n minus. It's positive roots and negative roots, and H is cartan. And corresponding Lie groups, let us denote them by n large plus minus 1. So, for example, in type A, let it be GLN, not SLN, and we have this group n plus. It's unipotent upper triangular matrices with units on the diagonal. And for type S, well, for type C, let us fix our symplectic form, our skew-symmetric form, which this group conserves as this one, a block matrix n by n, and we have the alternative diagonal. We have ones here and minus 1 here. So this P is just a matrix on ones on the alternative diagonal. And this one has n ones and n minus ones. Yeah. And in this case, this n plus is also a group of unipotent upper triangular matrices, but special form, which is also a block matrix. This matrix A has ones on the diagonal. This one also has ones on the diagonal, and this one is arbitrary. But those two are connected. And also we have on our Lie algebra a Cauchy involution, and we have a maximal compact subalgebra. And let us denote this by K. And the corresponding Lie group, Lie subgroup, K, the maximal compact subgroup in our Lie group. And for type A, there's just unitary matrices. And for type C, it is a unitary matrices of special form. So unitary, which are also symplectic. So, and let us note here that here we have in both cases, and even for B and D is also, it can be chosen as well, that both, that all n plus matrices will be unipotent and will have units on the diagonal. And also here, we can always choose our compact subgroup in the same way that all the matrices will be unitary, but with some special restrictions. Okay, and now we need to have our manifold when we have the action of Lie group. And a natural way to choose it is a cotangent bundle to a Lie group with a clear Lie theoretic origin. So it always can be trivialized, so we can just see it as a direct product of group and a dual to Lie algebra. And it has a natural symplectic structure here, which depends on trivialization, but if we choose left trivialization, it will be like this one. So it is a symplectic manifold, so we have a symplectic form, and we also have a Poisson brackets here. So, and Poisson brackets on X's on element of a dual to a Lie algebra, just a Lie algebraic brackets, and all group elements, all matrix element of group elements will commute to these Poisson brackets. And here we have something, but we will not need it. Yeah, but we have this symplectic manifold, and we have a natural action of a Lie group on its cotangent bundle. So we can consider left action of a group on itself or right action of a group on itself, and it can be lifted to an action of a Lie group to its cotangent bundle. And also these actions, if Lie group acts on a base, it always can be lifted to a Hamiltonian action on a cotangent bundle. So here we have a left action of a group on itself, and it can be lifted by just trivial action on a fibers, and it is a Hamiltonian action. And for right action, we need some coadjoint action of our group on the fibers to have a Hamiltonian action. So, and one can easily check that, for example, this alpha or this symplectic form doesn't change if we make this action. But this action not only conserves the symplectic form, but they're also Hamiltonian. And one can write the momentum maps here. And momentum map here will be just coadjoint action of our group element, which is coordinate on a base on our fiber coordinate, and here just a minus fiber coordinate. Yeah. So we have these two natural actions of our Lie group on its cotangent bundle. And we can also choose subgroups which acts on the same phase space, on the same cotangent bundle. And if a subgroup acts, it also acts in a Hamiltonian way. So, and let us choose. Yeah. So that's why it's a trivial action on the fiber. Yeah. So we can use also subgroup section. And this section will be also Hamiltonian. And let us choose and plus, which is unipotent upper triangle X from the left. And K, which is maximal compact, left acts on the right. And we have also Hamiltonian action, which also has momentum maps. These momentum maps are just projections on the corresponding dual spaces to the algebras plus and K. So in the projections, in the sense, so we have two decompositions. When we have the algebra, we had two decompositions and plus H plus and minus. So it's just a projection. Choose all H part, all cartan part, and N minus part to 0. Remaining will be N plus. And here as well, the projection to the K star just bring this decomposition, which is K plus P and P part to 0. Yeah. And let us use our trace form to identify this dual space with the Lie algebra and minus, and this to Lie algebra K. Let us just do this in the identifications. Yeah. So we have this symplectic manifold, and we have an action of N plus times K. So let us fix now the value of the momentum map, which gives us a Toda system. So this is an old construction given by Ostland a lot of years ago, probably 50. Let us choose here just a sum over simple roots of our Lie algebra as a momentum for N plus. And for K action, for compact action, let us choose 0 moment. And why we choose this one? Because here we have a maximal possible stabilizer. So 0 under co-adjoint action of K is obviously stabilized by the whole K. But also if we have sum over simple roots, even with some coefficients, arbitrary coefficients, it will be stabilized by a whole N plus action. Because we cannot obtain a simple root as a commutator of two other roots. It can be obtained just by commutator with cartan, but we don't have a cartan here. So, and we have a group N plus times K acting on our cotangent bundle. And we have a stabilizer which is also N plus times K. It cannot be larger. And our reduced phase space will have the minimal possible dimension. So we have a maximal stabilizer, and our dimension will be 2 times rank of our legal gem. So, and we need here only rank of our group integrals for integrable system. So we started from a phase space which is 2 times the dimension of our Lie group, and now we have 2 times rank, which is much smaller, and we need only rank G integrals for our integrable system. Capital K is a maximal compact Lie group, which is unitary or some subgroup in unitary. Yeah, and we have here some sets of invariant functions which are commutative on the top. So we have our x, and under this action of n plus times k, it is just a co-adjoint action of a compact Lie group, or adjoint action. It is the same. Yeah. So, and we have some adjoint invariant polynomials of this x, and the number of these independent adjoint invariant polynomials, it is explicitly the rank of this Lie group. So, and here we have, for example, traces of XL in the matrix representation. And we have these rank G functions, which are invariants. And traces of X in the power L are just Casimirs, or this add invariant polynomials are also Casimirs of this Lie algebraic bracket. So they commute on the top. So we will have an integrable system on the bottom. And another set of commuting variables is this one. Let's have this Lie group element and its conjugate. And let's consider our L times L minor of this element from the right bottom element. And we have this action. We have action on G, which is n from the left and k from the right. So k is a subgroup of unitary group. So we have one here. So we will have that just an action of n from the left, and it's conjugated from the right. And it is the upper triangular matrix with the units on the diagonal. And this one is lower triangular matrix with units on the diagonal. So all the minors, right, lowest minors of this matrix, G, G, and cross, are n plus times k invariants here. And in the structure of cotangent bundle, we have the Poisson structure that all elements of G commute with all other elements of G, so they trivially commute. So we also have here rank G invariant commuting elements. It also can give us an integrable system. Yeah. So, and the first set gives us the Toda chain. And how to see it clearly, we need to use this gauge freedom of n plus times k. And it is called Toda gauge. So let us use this action of n plus times k to diagonalize the matrix G. It can be always done due to Iwasawa decomposition of Lie group G. So this element of group element can be decomposed into a product of upper triangular times diagonal times unitary in A case and more complicated in BCD, but still of the same form. So n from n plus, A from A, and k from k. So every element can be represented in this way. It's global decomposition of our Lie group. So, and this subgroup A has a real dimension equal to rank of our Lie group G. Even we have a complex Lie group, but A has real dimension equal to rank. So we can use this decomposition, and we can use this action to make all G's diagonal. So, and let us denote this like this. So we have, let us introduce some coordinates, rank G coordinates here, and HI is just a Cartan elements in the algebra. Yeah. So now G is diagonal, and one can easily solve these equations in this gauge and describe this phase space. So the projections to k is equal to 0. X has this form, and this p is Cartan part, which cannot be determined by this momentum equations. So we have rank G more coordinates, and we have two rank G coordinates in our reduced phase space. So first rank G is Q, and others one are P coordinates on this Cartan. And they are also real because in this K, we also have in this compact Lie algebra, we also have a Cartan part. So we have only real coordinates here. And this x alpha can be determined from the second equation. So they're just exponential of simple root acting on this Q set of Qs. Yeah. So, and now we get this x. On the diagonal, it will be p coordinates. And out of diagonal, we have this part. Simple roots and negative to simple roots. Sorry, should be written here that roots are only simple. So we have, for example, in our SLN case, we have just a 3-diagonal matrix with a momentum on the diagonal and coordinates just above the diagonal, where the simple roots of SLN, and just below the diagonal, where the negative simple roots are for SLN case. And we have this invariance, traces of XL, on the top. They were just very simple things. They're trivially computed here. But now our X is not so simple, so we can substitute this here, and we will get rank G commuting integrals on our phase space, which are nothing else but integrals of Toda chain. But this J, L, which is minors of group-like element, they are just some functions of these Qs, and they are trivially computed. So we have an integrable system from the one set of commuting invariants on above. And from the other set, we have just a trivial system, just a trivial sets of coordinates which commutes due to Poisson brackets below. Yeah. Oh, simple, sorry, it's misprint. Yeah. When we solve here the equations. Yeah. So this one is from that equation. Yeah. So there's, here is for all positive roots. And here we have only simple roots in our element. So here, sorry, it's a few misprints here. Yeah, so and here is not 0, here is 7. Yeah, and we solve this element conjugated by a diagonal matrix. Yeah. So, and we got the Toda system from this reduction. And so how to get a dual system? We have two sets of our commuting functions. So let's choose the second set as a Hamiltonians, and let's see what will happen with the first one. So, and we need another description of our phase space. So we would like to have this axis to be simple. So let's diagonalize this x, because we have the action of k x. And due to this equation, for example, in type A, this x is a Hermitian matrix. So it can be diagonalized by unitary adjoint action. And it's also true for BCD as well. So let's diagonalize this x, and it is Hermitian matrix. It will have real eigenvalues. So we again have rank G coordinates. So, but we also have this n plus gauge symmetry. And let's use this n plus to make the matrix G lower triangular using Gauss decomposition. It is not global, but still, for the large set, it can be done. Yeah, so, and for example, for S-len case, matrix can be decomposed as a product of upper triangle with units on the diagonal to the lower triangle with arbitrary diagonal. So let's do this decomposition and use this n plus section to make this G just lower triangular. Yeah. And we used this momentum equation and this K action to diagonalize X. So we use this n plus gauge freedom to make G lower triangle. And let us now solve the rest. So we have a Cartan element, and a joint action of a Borel. So we have an element of Borel algebra. And the projection to n plus, or to n minus, sorry. So we just have a Cartan part, have n minus part, and Cartan part here is just X. So we can solve this momentum equation on the next slide, but it can be rewritten in this way. Yeah, so X is diagonal and G is lower triangle. And X's are diagonal, so it's just a function of the coordinates. And G is non-trivial, so we have some dual Hamiltonians here. Yeah. So let me first show how to solve it for type A. So we have a diagonal matrix X, and we have a simple roots which are just under the main diagonal, and ones here. And we have this momentum equation. Yeah, so for diagonal elements of G, we again do not have any restrictions. So we just denote it by AI, which are the other rank G coordinates here. And for the non-diagonal elements of G, we will have this recurrent relation. So the next one can be obtained from the previous one, starting from the diagonal. And we will have this G's be just a diagonal element multiplied by this 1 over Qj minus Qk. And we have so many multipliers, how far we are from the, yeah, so we just solved the momentum equation for type A. And what happens for type C? Almost the same. Yeah, we have this X, the diagonal matrix. So we chosen our Lie group, which can serve this anti-diagonal part. So we will have the root system, which is probably not so usual, but still we have Q1 and minus Q1 here, Q2 minus Q2, and so on. And here we have Qn minus Qn, and 0 on the. Yeah, so it's just a matrix representation of this in type C. And simple roots in this representation are also just ones and minus ones just below the diagonal. And we have n minus 1 ones here in this block. We have n minus 1 minus ones here in this block. And in that block, we will have only one non-zero element, which is 1. Yeah, which is a special root in this type system. Yeah, and again, we have our element G, our group element. So we also used the freedom to make it lower triangular. And let us fix the diagonal part here. And we will fix the diagonal part here. And it will automatically fix the diagonal part in this block, because we have only rank G independent values. And we again, if we fix the diagonal elements, we will have some recursive relations which also allow us to obtain the non-diagonal elements from the diagonal ones, just one by one. And for this part, for this A, we just have the same as for type A. And for this matrix C, it is a little bit complicated, a little bit more complicated. So for this A, we have the same, and for this C, we have almost the same, but we also have sum over 1 over Q plus Q, not only Q minus Q. Yeah, so this is a solution for type C. So now we have this explicit form of this lower triangular matrix, but it appears that it is a very nice form. We can compute all these minors explicitly. We can compute all the Hamiltonians of this goldfish system explicitly. Yeah, and we need to use Cauchy-Binet formula to do it. So we have a minor L times L minor of some larger matrix, which is probably 2n times 2n or n times n. Yeah, but we need only L by L minor. So it can be computed using Cauchy-Binet formula. So here M can be n, 2n, or even 2n plus 1 for big case. So, and this determinant, this minor of this product can be interpreted as a minor, as a determinant of a product of two rectangular matrices. It can be computed using Cauchy-Binet formula as a product of the sum over product of determinants of just this L times L matrices in our rectangular matrix. Yeah, so here we will have some sum over sets of indices of size L, and let us choose the columns here with the indices S1 to SL, and here as well, and we will get this determinant. For this case, those matrices are conjugated, so we have just a sum over squares of modules of the determinant, so we do need to compute the sign of this determinant to find the value. And for this special matrix G, their minors have a very special form. They can be easily computed explicitly. So we have here, we have G, we have the same AG in the every column. So we will have here a product of A's. And all other terms are also packed into this product. Yeah. Yeah. And it is how it works in type A. So we have all the minors. Sorry, again, it should be a misprint. It should be a sum over squares of modules here. Yeah. And after that, we can do some change of variables to make this Hamiltonian looks like I write in the very beginning, which are connected with the rational Ruijsenaars system in the strong coupling link. We need to do some change of variables to bring them to the same form. Yeah. And it is how it works in type A. So we just decompose the problem. So we compute the minors of matrix G and use Cauchy-Binet formula to compute this Hamiltonian. And what happens with the type C, for example, and for B and D as well? We have this matrix 2n times 2n, and we need lowest right minors of this matrix. Yeah. So, and in a Cauchy-Binet formula, we will use only these two blocks here. We will never get the elements from here or from here in our determinants. And what is the way of doing here? So we can write these elements, and up to these signs, we have that this n lowest rows of our type C matrix or type B or type D matrix. For type D, it's a little bit more complicated, but for B and C, the same. That this matrix do not look like a GLN-like matrix, which was before, like A-type matrix. But if we consider only lower part, it looks like a GLN matrix, but we have two n variables A and two n variables Q. So, and for A, we need to have these A's and their inverse. And for Q's, we need to have this and their opposites. And up to some sign factors, this matrix, the lower part of this, is the same as a matrix for GL2NC, for the same as type A matrix for a larger type A matrix. So we can do these calculations as well and got the Hamiltonians for BCD types. So for example, if we do it, and if we do the same change of variables, we will get type C generalization of Goldfish model. Yeah. And other formulas are longer, so they do not fit here probably. Yeah, and it is how it works in type C. In type B, almost the same. And for type D, we have some trouble with the last Hamiltonian, but it can always be computed explicitly. Yeah, and so let us review what happens here today. So I show you the general construction of Ruijsenaars duality between Toda systems and another interaction system of particles, which is called Goldfish model. So here we have a system with a rational dependence on a moment and exponential dependence on coordinates. And here we have exponential dependence on moment and rational on coordinates. So, and it has a Lie theoretic origin, and it can be deduced from Hamiltonian reduction, and some explicit formulas for these Hamiltonians, for this reduced space, these Goldfish models can be computed in BCD types. So here we have formulas for Toda first non-trivial Hamiltonians in these cases. And here I wrote formulas for Goldfish Hamiltonians in these cases. Yeah, so that's all for today. Thank you for attention. Any questions? Microphone. Yeah. Almost directly, yeah. 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 Oh, yeah. With some additional work, yeah. 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 For C, it works like that, yeah. Yeah. Uh, which one? Blue square? Yeah. Here. Yeah. Yeah, it's some mistakes probably here. It's not 1-4, but it doesn't matter. You can shift the coordinates to make this term just be 1. Yeah. But yeah. Yeah. Actually, I don't know. There is some relation of goldfish with some integrable hierarchies, but probably not of this type. So it can be obtained as a pole dynamics, but I don't know about this way. Just extension to field theory. Sorry, I don't know. Should work, yeah. It should work. Yeah. So probably with some, yeah. For example, for BCN, it definitely should work. So the formulas will work, and probably some proofs cannot. Yeah. So I like physically, in the physical sense, so I can write some formulas of dual systems, but probably I cannot prove correctly for super algebras how it should work. Yeah, it also should work for relativistic Toda system, actually. And we will have two exponential dependencies here, and here we will have trigonometric generalization of goldfish, which is also on this set of dualities. But the proof also is not simple because we will not have a cotangent bundle on the top. We will have some moduli space of flat connections, or G times G on the top. And it is not easy to prove it, but it should work. So, but we believe it should be proven. Yeah, and also we believe that it will work not for only integrable case, which is just a Toda system, but for full Toda system as well, which is a super integrable system. And we will have something like spin goldfish model. Yeah. And with some strange Ruijsenaars duality of super integrable system, which works on this integrable part. For affine case, A1 affine is known. We know that the dual for a closed Toda chain with two particles is a system with elliptic dependence on momentum. So, and it is some limit of double elliptic system. But yeah, A1 hat. I believe only this is known. So we can postulate that there should be some systems, but probably I have never seen any proofs. Yeah, but the hypothetical systems with elliptic dependence on momenta exist. Okay. No more questions. So let us finish our seminar.